Okay, thank you. I thank the non-local organizers for inviting me to speak and the local organizers for running this. Now, I decided to give a talk, which means that I can't put up pictures of people. But if I were, then I would put up a picture of Ben Hayes and Sri, but I don't need to because they're right here. And also, like a lot of this work was motivated by a bunch of conversations with Isaac Goldring and with his student Jennifer P. So, what I'm going to talk about is specifically related to free entropy. Of this talk. And so I'm going to start out by reviewing the definition of free entropy. And I know that this definition is a bit technical, but bear with me. I will, later in the talk, I will highlight what you need to take away from this. So in free probability, we talk about the star distribution or star law of non-commutative random variables. So maybe I should start out by saying, so given some von Neumann algebra with a faithful normal tracial state, and given some x, so I'm going to take an x will equal to a tuple. So I guess in this talk, maybe I'll consider finite tuple as well as infinite. And so then the star law, or also known as the star distribution of x, is the map from the non-commutative polynomial algebra, which let me call it Ux. The non-commutative polynomial algebra in certain variables, say tj. So this is for the infinite case, infinite tuple. You take a polynomial and you map it to the trace of t of the form x. Right. So then we can look at the space of non-commutative laws. That's a very important object for looking at free entropy theory and a bunch of other things. So given, and I'll pick a certain bound. So let's say R will be bounds like this, and then the sigma R will be the set of say mu x, where x is from some tracial von Neumann algebra, and the operator norm of the xj is bounded by rj. So this is all the non-commutative laws where the operator norms are bounded by r. And one can show, if you want, that this is equivalent to sort of traces on universal C-star algebra of generated by some x's with this bound. And so in particular, this is like a nice, so this is a nice weak star compact convex set. And I enjoy using this perspective because, like this, if you consider it as a topological space, it's a nice compact Hausdorff space. It's metrizable. You can do a lot of point set topology type arguments. Okay. Now, how do we define the free entropy? So here I'm going to give. Okay, so this is, I guess, Gillespie. I think the third free entropy paper where he discusses free entropy in the presence of the von Neumann algebra. So let's say that we're given, and I'm going to assume that this time that the x is a finite tuple, and the y is like infinite tuple, countable. And we're going to assume that x and y generate our polynomial algebra. And again, tau is our faithful normal tracial state. And so so free entropy is sort of defined by you look at the space of the set of matrices which have approximately the same non-commutative star law as the x's. You take Lebesgue measure of these spaces of matrices and you look at the kind of the exponential growth rate of these things. But here I'm going to define entropy in the present, so what I want to study is matrix approximations where not only do they approximate the non-commutative law of x, but also there exist other matrices which together with the models for the x will approximate the non-commutative law of x and y. So that you're sort of simulating having the generators of M also be somewhere in the picture. So the way this can be written down, well, so you take for say O, which is a neighborhood of the law of xy in this space of non-commutative laws. So we're assuming that this tuple R gives you operator norm bounds for the x and y's. And then you define this microspace space. So this is exactly this space of matrix approximations. And this would correspond to, let me say, I don't know, hopefully I don't regret this, but x tilde and y tilde, and this will be in the n-byte matrices, but then you'll take like you'll assume that each of them is bounded by Rj. So you like take the Rj operating norm ball of the matrices and you take the product of those. So then you have an element from there. And then you want to say that the star law of this is in the given neighborhood of the law of the x y. Okay, so those are matrix approximations for x and y jointly. And then what I do is I take these matrix approximations and then I project them onto the first d coordinates in order to get out the matrix approximations for x. So these are all the matrix approximations for x for which there exists some compatible one. So that's now the space of approximations for x to study. And then you take the log of the volume of this. We have some normalization. Don't worry about the normalization, it's fine. And then you take this. Okay, so then this is sort of studying the exponential growth rate because you took the log and then you're taking this limit with the appropriate normalization. And then after that you take the infima over your neighborhoods. So this is the free entropy of the x in the presence of x.
David, I think you also want d goes to infinity.
No. So I'm fixing x. X is fixed.
Oh.
It's a d tuple, right? But now I'm allowing infinite tuple of y's. So yeah, Voiculescu only did finite tuple of y's and then took the number of y's to infinity. But you can just do it this way too. Okay. Right. So I guess the remark is that you can replace lim sup with a limit on ultrafilter. So this will be an ultrafilter, which will be an ultrafilter on the natural numbers. That's a non. And an intuition for this is that this thing here is sort of measures the amount of embeddings and this will be the ultra-filtered version. This amount measures the amount of embeddings of the von Neumann algebra of X into matrix ultraproduct associated to U that extend to embeddings of M. That's intuition for this. Because that every time that you have a sequence of microstates which are getting into closer and closer neighborhoods of the law move, then that you'll be able to use that sequence to define an embedding into the ultrapower. And so it's sort of by measuring the number of approximations at each finitary level is some kind of way of quantifying how many different ways there are to embed. And the fact that you demanded that there exists such a Y like this is sort of demanding that this extends to an embedding of M. Let me see. Okay. Great. So that's the basic setup. Now I can state the theorem. Okay. So now here's the theorem. Okay, so suppose you're given n tau, let's say n is separable. X is an m to the b. Then, if your free entropy with respect to this ultrafilter in the presence of m is non-trivial, so it's not minus infinity, then there exists some trace preserving embedding from M into, let's call the embedding iota, and it's into, again, this matrix ultraproduct. Such that the entropy of the image of X in the presence of the matrix ultraproduct is the same as the entropy of X in the presence of M. Okay. So, why is this, what is this saying? Like, why is this even a theorem? Well, no. In general, right, the entropy of iota of x in the presence of q would be less than or equal to the entropy of iota of x in the presence of iota of q for any embedding. So any embedding that I choose is always going to have at most as much entropy. Why? Because here I'm looking at approximations where I demand that there exist things that simulate the generators of M. But here I'm looking at approximations where I demand there exist things that would simulate some, well, I guess Q is not separable, but you consider any tuples in Q, and you would demand that for any given tuple in Q, there would exist, for any given tuple in Q, you would look at the microstate spaces where you demand that there exist things simulating these generators in Q. And there's a lot more stuff inside the matrix ultraproduct than just inside M. Right, so here I'm saying you can add in a lot more conditions that there exist things that are simulating arbitrary elements of the matrix ultraproduct Q, and still have just as much entropy as you do. And maybe just one comment on why would you even care about this? So Voiculescu again. I think it is. Okay. I don't know. I think it's 1996 because that's what I wrote. But prove that, okay, so if the presence, or if the entropy of x in the presence of M is non-trivial, then the commutant of W of the von Neumann algebra of x inside M is trivial. And in fact, it also, the same reasoning also showed that there aren't, the same reasoning also showed that for an ultraproduct, the commutant will be trivial. Right, if you take, so there are in fact not any sequences in M that asymptotically commute with the von Neumann algebra. So Voiculescu showed this result here, and hence something like this would imply that that inside the matrix ultraproduct here, the relative commutant is trivial. And so in particular, this means that that this iota from M into Q is being reduced.
David?
Yeah.
Do you need M as diffuse?
Well, this is automatically true. Like maybe, I mean, I'm assuming that I have at least two variables. Yeah. I mean, if for one variable, well, actually, no, see, I'm doing it with non-self-adjoint variables, so it's already at least two self-adjoint variables. So this is simply true. And I think if you look at the techniques in Voiculescu's paper, and by the way, this is very similar to a paper of von Neumann before that was showing something that, something like there exist matrices such that there isn't such that there, basically for a random choice of a matrix that's non-self-adjoint, there's very little in the matrix algebra that almost commutes with. And so the same technique was in Voiculescu's paper. And I think you can probably show the existence of such an irreducible embedding using the technique in Voiculescu's paper. But this statement about the entropy here is strictly stronger because basically it tells you anything in the Q. You can have microstates simulating anything in Q here and still have the same amount of entropy. So I gotta tell you how to prove this. And basically, well, I'll sketch at least. The idea is some sort of probabilistic argument. Basically, like we have, you have all possible ways of embedding it, but then within that we could kind of break it down in a finer way by looking at, for instance, the orbits of the embedding under the action of automorphisms. And then we might want to say that, well, if the entire space of embeddings is this big, then there must exist some piece of it, which is that. Too bad. I had to erase the definition.
David, I have a question about the definition. So, you said that you can replace lim sub with limit along an ultrafilter.
Well, I'm not saying you would get the same answer.
Okay.
I'm saying that's another thing you can apply. We do not know whether you get the same.
Right.
Okay. Right. So, you have a picture like this. So now you have all your embeddings. In Q, which extend to embeddings of M. And then you have like the automorphism of Q. And if you had an automorphism of Q, right, and you had an embedding, you could consider decompose with that embedding and get another embedding. And so you have some sort of orbits here. Orbits under the action of these automorphisms. And so what I'm going to do is get something that doesn't just measure the size of all the embeddings, but actually will measure the size of each automorphism orbit individually. And this is where model theory kind of enters the picture. So the model theory tells you that, so assuming continuum hypothesis, given x and y, you can say this matrix ultraproduct to D, then the following are equivalent. One, that there exists an automorphism that maps the tuple x to the tuple y. Each coordinate gets mapped to the corresponding coordinate, right? So phi of x1 equals y1 and so forth. And secondly, that x and y have the same type. So this type in Q of x is something called the type of x. Okay. Now what is this type? Well, it's a little bit complicated to describe what the type is, but basically, instead of just looking at non-commutative laws where you look at the values of traces of polynomials, you would look at more complicated formulas that involve taking other operations, like taking supremum or infimum over operator norm ball and some other variables. So, in order to define the type, you have to talk about model-theoretic formulas. I'm just going to give a rough definition. Wait. Yeah, so formulas are created recursively by various operations. So first of all, we have basic formulas, which would be like the trace of some polynomial of x. So when we write the formulas, we usually specify which algebra you're evaluating it in, and also which tuple of operators you're doing. And so then secondly, if you're given formulas C1 to k, and you're given some f from r to the k to r continuous, then you can create a new formula which is f composed with these. So for instance, you could take f to be the map that does multiplication, and so then you could take two traces of different non-commutative star polynomials, multiply those two traces together, and then that would be available. And third, we have these operations of super. So if C of, say, x1 through xd, and y is the formula, you can define a new formula C. C of x, which would be there's a sup over y in, and so for a particular binomial algebra M, we take the take the supremum over a certain operator or ball, and of the original quantier. And then you could also do int instead of super. And so then by iterating these operations, this defines the formulas. And so then I'll call we could call f d, say formulas in d. And then the type, I want to do this before I iterate, so okay, the type in M of x is going to be a map from the space, from the vector space of formulas into, I guess I should take real numbers here, because I want to take super ints, I have to make it real, so I'll do real parameters. And it takes a formula, so the type will map this formula to the evaluation of this formula on x. Sort of like the definition of non-commutative law, but for these formulas. So then what you can do is define a version of free entropy where you use these types instead of non-commutative. So again, you can define a space of types, we'll denote by this. SD, which will be the space of types of B tuples, and then you can have a certain down on the radius as well. And this is another thing, it has a nice V-star topology, compact by, well, I guess the compactness theorem in model theory basically tells you that this will be compact.
Is it important that you have uncounted many formulas, or can you restrict to a countable subset?
Well, this is why it's metrizable, because you can find a countable dense subset of formulas. Because you can like you can just use radii that are rational when you take the suprema and infimum, and you can approximate with f. The f could be a polynomial with rational coefficients. The trace polynomials, again, like you can take those with rational coefficients and so forth. Well, rational with the I. Right. And so then we can just proceed in the same way as we defined for the entropy. So again, for neighborhood O, type, you define again it's microstate space, and this will just be X tilde in matrices to the D with the appropriate bounds, and with the type, right? So since the matrices are a tracial von Neumann algebra, you can look at the type of this thing in the matrix algebra. You just want to look at which types, matrices where the type is in this neighborhood. And so then you can define sort of version of pi, which will write full because it's the full type rather than just the quantifier free type. Quantifier free type is what you get from just the non-commutative law. This is still entropy of x, and it still kind of depends on the ambient algebra M, because the evaluation of the type depends on entropy M. And anyway, you define it in the same way as the other type of entropy. You just take the Lebesgue measure of this, you take the log, and you do the normalization and the limits and so forth, and then you take the infimum over these neighborhoods. Okay. So then the game is to relate this entropy for the types to the entropy to the original entropy. And there's going to be a sort of variational principle that does this, that says basically if you have so if you forget about independence for a second, if you have a quantifier free type, this entropy, maybe I'll just write this down first. Right, so it turns out this entropy of x, the quantifier free version, we only use just look at the moments of x. Don't worry about in the presence for the moment. This turns out to be the max over types. Let me say nu in the space of types, such that nu restricted to the quantifier free. You'll say, yeah. So the restriction of nu to the quantifier free formulas is just the law of x. And then, so you take the maximum of these, the entropy of these types here. And so this variational principle allows you to go from one to the other, and this is ultimately how this theory works. First, use a variational principle to get a full type that has the same entropy. And then, once you have that, you just argue that it creates an embedding into the ultraproduct, which is a sort of standard type of argument, I guess, in the spirit of diagonalization arguments, if you wish. But then, okay, so I think I'm going to tell you first, though, before getting to why this variational principle is true, I'll tell you how the entropy in the presence comes into the picture. So, the entropy in the presence incorporates a little bit more information than just the quantifier-free type of X, because you want to show that because you care whether there exist things which are simulating the generators Y for the von Neumann algebra. And the existence of such a thing is precisely captured by what is called existential formulas. So let's say that you're, so let's again say that you're given X, which is X1 through Xp, and you're given Y. And then let's say that you have some neighborhood of the quantifier free type or of the law. So then you can kind of create some quantifier free formula. Okay, so maybe for special choices of neighborhood or something, right? But basically, such a neighborhood will be given by if phi of x and y is positive, then the law of the x and y will be inside that neighborhood. And so then, what you can do is then you can define the formula, which is now a formula only depending on x, where you take the infimum of, I guess, y in the product of the corresponding operator norm balls of phi of xy. Let me write this because to distinguish it from the x and y that have been fixed. So you can define a new formula like this, and this, let me do it the other way. I guess I want to do it the other way. So say this formula being less than c means that the law is in this neighborhood. And then if you define a new formula like this, well, if the infimum over the y tilde of this is less than the c, then that will mean that there exists some y tilde which makes this less than c. And so sort of this captures the existence of the y's that kind of are compatible with the x's and simulate those generators. And so the so what it boils down to is basically the entropy in the presence studied by Jekel corresponds to a version of entropy for the existential type. Okay, well, it turns out. So given, given the same setup that we have here, let's say. Okay. So these types of things here are what we call existential formulas. Where you just have one quantifier and it's the inf. And so the existential type is this map which sends the existential formula to its value at point x. So then for the, so then we have this map. If you take the full type, then you can kind of project it down, restricting it from all the formulas to just the existential formulas. And this is like sort of a restriction, and this maps the space of full types into the space of existential types. And then, I mean, you can go look at the quantifier free type if you wish, right, which just corresponds to the non-commutative law. So now here's the result to relate the existential type, the entropy in the presence, to the entropy for the full type. So let's say that for mu, which is this existential type, let's say that mu is equal to the existential type of the x. Well, then we set this set k mu, and this is going to be mu in the space of existential types, such that nu of each formula is less than or equal to nu for b in the existential formulas. But what this is basically saying is that whatever things exist for the type mu will also exist for the nu, but for nu you might have more stuff, because you might be able to get a smaller entropy. And so then the result that we can get is that the entropy of the x in the presence of m is the maximum over the nu, which is full types, which project down into the set k mu, and we take the maximum of the entropy. And this will lead to the theorem, because because you can pick some full type which has the same entropy as mu, and then the full type sort of represents an automorphism orbit of something in the matrix ultraproduct, and something from that automorphism orbit with the embedding that you want that has the same entropy. Okay. I guess I have very little time left, but let me tell you basically the steps for this. So the first step is okay. So you can sort of define entropy of a closed set. So this time for k mu, and it's basically the same definition as before, except that you take the infimum instead of neighborhoods of a point over a single type, you take neighborhoods of this closed set. and then you take the corresponding limit of the log volume of these microstate spaces and so forth. So then the first step is basically to show that this entropy here in the presence, which only cares about the existential formulas, actually equals the entropy for full types of this set. And the reason for that is basically that, that you can create like a sequence of neighborhoods which are shrinking to this set K mu. And then, if you take the pre-images of those under this projection map, then you'll get a sequence of neighborhoods that are shrinking to the pre-image here. And because of the compactness, you don't have to take the infimum over all O. It suffices just to take a sequence of O whose intersection will be the closed set. So that's kind of the first step. And then the second step is that the entropy of a closed set, as defined here, will be the maximum of the entropies of the individual points in there. And the proof of that is sort of a compactness argument. So, so first of all, the entropy is upper semi-continuous. Well, yeah, maybe you don't need that, but okay. So you consider this set, and you consider the supremum of this thing here. If you have a constant c which is bigger than the supremum, then for each nu, there's going to be some neighborhood for which this limit will be less than that upper bound. And that's an open neighborhood. We have one for each point, so they cover this compact set. So then you can get finitely many neighborhoods. And each of these finitely many neighborhoods satisfies that this quantity is less than our given upper bound. And if you take the Lebesgue measure, right, the Lebesgue measure of the union is less than or equal to the sum of the Lebesgue measures. But we're not just taking the Lebesgue measure, we're taking the log of it, and then we're dividing by 1 over n squared. So if you just add up finitely many, a fixed number of things, this isn't going to affect the exponential growth rate. The exponential growth rate will just be the maximum of them. And so this is why this is true. See, I have like 1 minute left. We just maybe I'll make some remarks without trying to erase it. So this is what a version of the free entropy for full types. But you can also do the same thing with the one-bounded entropy, which came out of the work of Ken Lee-Chung, which Ben Hayes wrote up in his 2018 paper. In that entropy, instead of taking the Lebesgue measure of the microstate spaces, you look at covering numbers. But it's exactly the same modification can be made. Instead of using the regular old microstate spaces for the non-commutative law, you can replace it with microstate spaces for the types. And the one-bounded entropy has nice invariance property, namely that if you take an x and y, and they generate the same von Neumann algebra, then the one-bounded entropy of x and y will be the same. And so the same type of argument would work for the model-theoretic version. But you also have something nicer, that if you take this h, and then if you take the so-called algebraic closure in a model-theoretic sense of certain maybe A inside of M, then this will be the same as the entropy of the A inside. So algebraic closure maybe if you just think about what that means algebraically, it may mislead you, but what it means is that in model theory is that something is in the algebraic closure if there's sort of a, if there is a compact set, if it lies in some compact set, which is defined. So it would be a set that's compact in both. So for instance, you could think about this as in Galois theory, like you have a field and something is algebraic. So you could look at your definable set, which is the set of roots of some polynomial, and then there's finitely many things in that set, and then each of those things is in the algebraic closure. So for continuous model theory, it's the same thing, but here you want to have a definable set which is compact instead of finite. But compact things are basically things that are approximately finite. And you can kind of use this and use sort of similar compactness arguments to show that you get the same answer. Now, I don't know exactly what to do with this yet because we have very little understanding of what the algebraic closure is in any examples. But nonetheless, it appears that this is a very natural thing to study, and so this model-theoretic entropy for types, especially the one-bounded entropy version, appears to have a lot of applications. I guess maybe I should also say one more result based on this study of the model-theoretic one-bounded entropy, that you can conclude that the one-bounded entropy of a matrix ultraproduct is infinite. And it's because of basically this this same sort of principle here, but for the one-bounded entropy version. Because there exist things that have or even just like this, right? If there exists something in here where the entropy in the presence of m is finite, then that will imply that the one-bounded entropy of it is plus infinity, and so therefore this says infinite one-bounded entropy. And I should also note that if you take ultraproducts of R, this thing is not true. Because this thing has property gamma, so the one-bounded entropy of it is 0 by results of Ben. And so, but for this matrix ultraproduct, this thing is infinite. And so a lot of Ben's results about indecomposability things for something that has positive one-bounded entropy, right? These now can be applied to the matrix ultraproduct. Okay. Thank you for your attention.